What is the matrix? Unfortunately, no one can be told what the matrix is. Wait, that's not true. I'm going to tell you right now. In Leadwerks, a 4x4 matrix is a mathematical structure used to represent an object's position, rotation, and scale in 3D space. It's a way of compacting all of that information into just 16 numbers. So with 16 numbers, we can store an object's position, its rotation, and its scale on all three axes. So the mat4 class, that's the class that we use for 4x4 matrices. And it's called the 4x4 matrix because it's made up of 4 vec4 values. These are referred to as I, J, K, and T, or you can get them by index. So that's how you construct a matrix. You just use the constructor like that, and that's going to give you the default matrix if you supply 1 to it. And then you can get the each row of the matrix. So a matrix is made up of rows and columns. And the first vec4 is this row. The second vec4 is this row. The third vec4 is this row. And the fourth is like this. So let's just copy this code here and paste it into main.lua, and we'll run this and see what it prints out. And this gives us this interesting pattern here. I'll bring back the web page so you can see it a little bit easier. This right here. So the first row is 1, 0, 0, 0. The second row is 0, 1, 0, 0. The third row is 0, 0, 1, 0. And the fourth row is 0, 0, 0, 1. That's called an identity matrix. What do these numbers mean? The first row is, well, the first 3 numbers here, that's the object's x-axis. The second row here, this indicates the object's y-axis. The third row here, these first 3 numbers, this indicates the object's z-axis. And the fourth row, these 3 numbers here, that's the object's translation or position. What are these numbers on the right-hand side? For entity orientation, these are always just 0, 0, 0, 1. They're not used, but they need to be there for the math to work out right. Now, you might not deal directly with 4x4 matrices at all when you're doing game development. This might just be, this is how things are stored internally. This is how the object's orientation is stored. This is considered the real orientation that everything else refers to. So you might not use 4x4 matrices very much, but it's cool to learn about them, so I will tell you. We also store the scale in these, and the scale is just the magnitude of this vector. So if the entire object was scaled to be twice as big, then this first row would be 2, 0, 0, 0. The second row would be 0, 2, 0, 0. The third row would be 0, 0, 2, 0. And the fourth row would still be 0, 0, 0, 1. This is always 1. This right column is always 0, 0, 0, 1. So we'll take another look at this. This is the x-axis. This is the direction that the object's y-axis points in. And this is the direction that the object's z-axis points in. And then finally, this is the object's position. So by default, an entity's orientation is going to be oriented to the world coordinate system. So the x-axis is going to point in the direction of 1, 0, 0, 0. 1, 0, 0, which is the x direction. If we start moving things around, then we'll get different 4x4 matrices. And there are some exercises here you can do if you want. It's not that important that you understand what the numbers are. I would just like you to know that what these rows are, because once you understand that, then that's very simple and you can work with that. This also gives us a way of copying one object's orientation to another. We can get an object, we can get an entity's matrix, and then we can call set matrix to set another entity, and then instead of calling set position, set rotation, and set scale, we're just doing it all in a single command. Now, if you know, since you know what these matrix rows are, if you want to find out what is the object's forward direction, you can do that with this line of code right here. It'll just be forward equals entity.matrix and then 2, because we're getting the third row and they start with 0. And then we just want the first 3 numbers. So we're just going to get x, y, and z. And this is going to be the forward vector. Now that might be scaled, so we might want to normalize it just in case that it's scaled. But that's one way you can get the entity's forward vector. You can also call transform normal 0, 0, 1, which is the forward vector, and you can transform that from the objects, from the entity space to world space if you want. But this is another way to do it. So you can get the right direction, the vector that the object's right side is pointing to with this code. You can get the up direction with this code. You can get the forward direction with this code. And you can get the object's, one alternative way of getting an object's position is just to call entity.matrix and get the last row and just get x, y, and z of the last row. That's one way to do it. You don't have to, but I just want you to understand what the matrix actually is. So I have an example here that's going to use all of these techniques. So I'll paste it in. Let's see what this does. Okay, so we've got 2 ships here, and we are displaying the matrix information for the ship on the right. So its right direction is 1, 0, 0. Its up direction is 0, 1, 0. Its forward direction is 0, 0, 1. And its translation, the matrix translation, is 2, 0, 0. So that tells us a few things. That tells us the object's position is at 2, 0, 0. It also tells us the object is not rotated because all of its axes align to the world, right? And we also know that its scale is 100% because the length of all of these vectors, each of these vectors, is 1. So you can see how I'm printing that information out. First I'm getting the ship matrix value, and I'm just putting it into a single variable called m because it's just easier to type. And then we're just printing out all the different matrix elements like that. And I mean, you're probably not going to need this in your game, but I just want you to understand what it actually is, because there are times when you might want to access these values directly. Now, if I move this ship around, you can see the matrix translation is changing. And if I rotate it, you can see that the right vector is staying the same, but the up vector and the forward vector are changing dramatically. So let's see if we can get it upside down. That's pretty close. So now you can see the up vector is 0, pretty close to -1, and pretty close to 0. So it's basically 0, -1, 0 when it's upside down. And the forward vector is now backwards too, because this is the z value and it's just about -1. Now if I hit the space key, then that will just copy one ship's matrix to the other. And that's just a way of copying the entire orientation in just one command. So I don't have to call set position, set scale, set rotation. I can just call set matrix and it will just duplicate that matrix and do all of those things all in one step. So that's really all you need to know about 4x4 matrices. There's certainly a lot more to them, but that stuff probably isn't important for games. One more interesting piece of information is all the transform commands we had, like transform point, transform vector. In addition to accepting an entity for the source and the destination, they can also accept a 4x4 matrix for the source and the destination. And in fact, that's how the engine handles it internally. So that's what the matrix is. And now you're ready to use them if you choose to.